On behalf of my company and myself, we're really excited to be here at ETHDenver. And we'd like to thank the organizers, the stewards, the volunteers, and the staff, everybody who's come together to make this event so great. Let's give it up. Octan Network is a data intelligence company. We do on-chain algorithmic reputation and other analytics. My name is Scott Imig. I'm a principal scientist at Octan. My background is from the web world, web search, paid search, recommender systems, personalization. So you'll see that flavor in this talk, both the data science flavor and the Web 2 flavor, but I promise to bring everything together for something that's very relevant to blockchain. So all right, everyone, let's get into it. This is the Octan business model. Our stack is in the middle. We have a distributed GPU compute protocol and a reputation ranking system. We're a B2B company, so other businesses pay us for services and analytics at different levels of the stack. This talk is about on-chain PageRank, and it's related to a blog post from Brian Armstrong from August 2023, where he gave 10 ideas for startups that he would found today if he was starting a company today. And they're very innovative ideas. Network states, flat coin. And among these 10 very innovative ideas is on-chain reputation. And one of the points that is made in that blog post and the video that went with it is that the web has exactly the same data structure as the blockchain. On the web, you have pages and hyperlinks between pages. And on the blockchain, you have addresses and transactions between addresses. So anything that can run on the web graph can run one-to-one on the blockchain without modification. In particular, PageRank can run on the blockchain and provide a reputation score just like it does on the internet. So to give some credibility to this idea, let's look at the sizes of these two graphs. The web in 2024 has 202 million active websites. Ethereum in 2024 has 205 million active addresses. The sizes are not just the same order of magnitude, they're almost the same number. Of course, there are differences. It would be nice to know more about the web topology, but that's a very difficult research problem, things like diameter and connected components. Because in order to know about the web, you have to crawl it. And the crawler is always behind reality because the web is always evolving. You contrast that with the blockchain. At any given time, we can know exactly the state of the blockchain. And not only can we know exactly the state of the blockchain at that point in time, but we can know the historical state of the blockchain at any historical point in time. And there are other important differences. In the blockchain, for example, the transactions, which are playing the roles of hyperlinks, have a lot more information. They have amounts. Higher amounts are more important. They have ages. An old transaction may be less important than a newer transaction. They have multiplicities. Two hyperlinks from the same web page to another web page doesn't carry the same importance as two transactions from the same address to another address. So all this goes together to kind of demonstrate that PageRank is not only applicable to the blockchain, but PageRank is more applicable to the blockchain and more powerful on the blockchain than it is on the Web 2. Let's just review and introduce the PageRank intuitions and maybe one or the other. PageRank is based on a random surfer model. The idea in the internet is that this random surfer, this hypothetical surfer, goes to a random web page. And then on that web page, they randomly select a hyperlink. And they go to the target page. And on the target page, they randomly select a hyperlink and go to the target page of that. And they go on forever. And if they go on forever, then at some level of approximation, the page rank is the percentage of visits that each page has. there's some additional components to PageRank. One thing is there are dark corners of the internet where the random surfer can get stuck. They can get into that dark corner of the internet, but they can't get out because there's no hyperlink getting out. So in order to account for this, PageRank allows this random surfer to jump with some probability. Usually it's set to 20%. 20% of the time, instead of following a random hyperlink, they will choose a web page at random and then go to that web page. And in the internet world, this is done with a uniform random distribution, usually. So all the pages on the internet are equally likely to be chosen. But it's not necessarily the case that it has to be a uniform distribution. This random surfer may, 20% of the time, jump to the same web page or to the same group of web pages. Or the random surfer may prefer certain web pages over other pages. This is called personalization in PageRank. And so it's possible not only to weight transactions by their amounts and ages and multiplicities, but it's possible to weight addresses by anything that you know about the address, maybe the balance at that address. This leads us to adapted PageRank. Blockchain has these features, and we want to incorporate that information into the algorithm. So we can weight nodes and edges according to everything we know about the blockchain. And this is not the first time it's been done, applying this to blockchain, adapting for blockchain. It's not the first time. For example, in city networks for city planning, some applications want to find the important intersections between city streets. But some intersections may have a big building on them, or some intersections may have a vacant lot, and some may have houses. So the features of the intersections are actually possible to incorporate into PageRank before PageRank even runs. And then let PageRank do what it does. This allows us to tune the PageRank algorithm using all of the information that we've been discussing to be very specific to a scenario, or to be very well tuned to the blockchain. So let's suppose that we adapt PageRank to the blockchain. And we've used all the math and all the intuition, and we've asked all the experts, and we think that this ranking for reputation based on PageRank and all the weightings that we've assigned is a pretty good ranking. How can we tell if it's really good? Well, if there are data scientists here, they'll tell you what you need is an independent truth set where you can take the reputation ranking and you can compare it against this independently generated truth set and see how the reputation ranking performs against the truth set. Fortunately, the blockchain excels in this regard too. For example, the Arbitrum airdrop did not go to every address that met the criteria specified for the airdrop. Certain addresses were eliminated. Some of them were eliminated because they were large, publicly known addresses and they weren't qualified for the airdrop. But some were eliminated because they were bad actors. They were spamming the network, and so they were disqualified from the airdrop. So using the Arbitrum airdrop, we can say that anyone who received the airdrop is true quality, high reputation. Anyone who didn't receive the airdrop is low quality, low reputation, and false. Or we could look at Etherscan. Etherscan actually has warnings for certain addresses. Such and such authority has warned that this address may be associated with a Ponzi scheme. So we could say that anything that has an Etherscan warning is potentially low reputation. We should treat it as false reputation. Anything else we can treat as true reputation. We don't really care where anything else falls in the ranking. We just want to eliminate any of these Etherscan addresses with warnings. Or the other way around. Maybe there's a large trusted entity. Let's say Uniswap. Uniswap has many addresses. And so we may think that a lot of people trust Uniswap, and let's say that we want to give high reputation to the Uniswap addresses. So we could give a true value to that. We could say that's high reputation, that's true reputation. And everything else can be false. It doesn't matter where anything else falls. We just want to be sure that the Uniswap addresses appear near the top. So let's look a little bit closer at the Arbitrum airdrop. How did Arbitrum detect the Sybils anyway? They used a clustering algorithm on the transaction graph. Clustering algorithms on large graphs can be very expensive. And so we can take the output of that very expensive operation and the existing reputation score and see how those two compare. And we can actually measure this and assign numbers to it and use the number to improve it. So the way that we can do that is rank all the addresses by their reputation score in descending order. The very highest reputation is at the top of the list. The very lowest reputation is at the bottom of the list. Everybody else is in order in between. And then suppose you were going to launch another airdrop on Arbitrum. You might want to use the relevance score, the reputation score, to determine which ones would receive the airdrop. So we can set a threshold where you think that above the line, those are pretty high reputation, and those should get the airdrop. Anything that's above the line and got the Arbitrum airdrop, we treat as a true positive. It's high reputation according to the reputation score, and it's high reputation according to the Arbitrum airdrop. Anything above the line that did not get the airdrop is a false positive. It's ranked highly according to the reputation score, but it did not get the airdrop, so it's a false positive. And the true positive rate is the percentage of the true positives, and the false positive rate is the percentage of the false positives. You can see that for different business scenarios, it could be very useful to adjust that threshold. Let's say that for your new airdrop, you wanted to be sure that everybody who possibly qualified for the airdrop would get it. And we don't really mind if a few bad actors also get it. Then you could set the threshold very low. You could capture almost everybody who's a good actor, and you also get a few bad actors, and for certain scenarios, that might be okay. Or the other way around, let's say that we really want to eliminate any Sybil attackers. We could set the threshold very high, and then a lot of people who were good actors would not get the airdrop, but we would at least not be getting a lot of bad actors with the airdrop. So the threshold can be adjusted for different business scenarios. And between any of these two addresses and this long, long vertical list of millions of addresses, there's actually a threshold. And that threshold has a false positive rate and a true positive rate. So being a data scientist, I love charts and graphs. And we can chart this, the true positive rate on the y-axis and the false positive rate on the x-axis. And this is known in data science as the receiver operating characteristic curve. You may have heard of it. Any data scientist will tell you this can be very useful for measuring the performance of a ranking. And the way that you use it to measure the performance of the ranking is that the percentage of the rectangle that's underneath the line is your score. So on the left, we have a lower quality ranking, and on the right, we have a higher quality ranking. There's 61% of the area is under on the left, and 84% is on the right. Now, 84% is a very good number. This is real data against the Arbitrum airdrop using Arbitrum reputation scores computed from before the airdrop. And if we were a pharmaceutical company and we got an 84% area under the curve, we would take that product to the next step. And if we were a web search company and we got an 84% area under the curve, we would take that model to the next step. So 84% is a positive result. It has a signal. And we can not only do that, we can not only do one experiment. This is just one experiment. We can do any number of experiments because we have transactions with amounts and ages, and we can adjust how we're weighting those transactions according to their amounts and ages. And we can also adjust how we're weighting nodes and improve on this score over and over and get that area under the curve higher and higher and higher. In the case that I'm showing from the previous chart, from the previous slide, we were actually experimenting with weighting nodes according to either incoming or outgoing transactions. And it turned out that one was much better. The other one had a signal, but this was much better. So there are a lot of opportunities to adjust this. So for future work for the reputation scoring algorithm, we are comparing these scores against other truth sets, other airdrops, and some of the other truth sets that I mentioned. There are also a lot of tools from the web that we can apply that are related to area under the curve, but other tools like precision at in. There are other analytics that are important. Maybe this high reputation address got the airdrop, but did they just sell the Arbitrum tokens when they got the airdrop and then stop using Arbitrum? Or are they still users of the Arbitrum? And can that reputation score predict that? We're moving toward decentralized compute for algorithms and visualization. This is a DPIN initiative. And we're moving toward decentralized Oracle for reputation. So this is my final slide. And I have an email address on here for inquiries. We're very interested in connecting with you. We're interested in connecting with partners. We're interested in connecting with customers. We're interested in connecting with investors. And we're interested in connecting with other engineers and data scientists who are interested in algorithmic reputation. I also have a POAP up here. And the POAP is on a piece of paper. And the piece of paper is my business card. And it has all my contact information along with this email address. So if you see me after the talk or you see me anytime during the conference, please say hi and I'll give you a POAP. So thank you for everybody's attention and have a very prosperous and good and productive week this week and at ETHDenver. And I really appreciate your attention. LFG.